In part 1, we saw the front half of the transformer. Text becomes tokens, tokens gain meaning and position, and self-attention mixes in context from across the sentence. If you missed it, the link is in the description. Each token now carries a context-rich representation. In this part, we'll see what the model does with it, and how all of this finally turns into the next token. After attention, each token vector has gathered information from the surrounding context. But gathering information is only half the job. The model still needs to make sense of it. That happens in the feed-forward network, a simple neural network applied independently to every token position. Attention is the communication step. Tokens look at each other and share information. The feed-forward network is the thinking step. It takes over right where attention leaves off. Each token already carries the context attention mixed in. Now it works on that context-rich vector on its own, without pulling in anything new from its neighbors. So the two steps form a natural sequence. First, gather the right information, then think hard about it. Here is roughly what that thinking looks like. The feed-forward network takes the token's vector and expands it into a much wider space. It applies a non-linear activation, which lets it capture richer patterns than a plain linear step could. Then it projects the vector back down to its original size. Each token goes in, gets reshaped through this wider hidden space, and comes out as a refined version of itself. And this matters for another reason. Attention on its own is mostly a weighted average, a fairly linear operation. Without this non-linear step, stacking attention on top of attention would not add much power. The feed-forward network is what gives each layer real expressive strength. In modern transformers, this part is only a couple of layers deep, but it is very wide. So even though its structure is simple, it often holds a large portion of the model's parameters. That makes the feed-forward network far more than a minor detail. It is where much of the model's internal transformation actually happens. And because this pair repeats in every block, the model keeps alternating. Communicate, then compute, communicate, then compute. Layer by layer, that is how meaning builds up. Together, attention plus feed-forward forms the core of a transformer block. Attention and feed-forward networks do the core computation inside each transformer block. Attention lets tokens exchange information. The feed-forward network transforms each token representation. But one block is not enough. To build a powerful language model, transformers stack these blocks again and again, sometimes dozens of layers deep. And that depth creates a problem. As information passes through layer after layer, the signal can become unstable. It can fade, it can grow too large. And during training, the gradients that teach the model can become harder to control. So every transformer block needs two stabilizing pieces: residual connections and layer normalization. A residual connection means the block does not completely replace its input. Instead, it adds an update on top of the original vector. So the original information can keep flowing forward, while the block adds something new. This makes deep stacks easier to train, because information does not have to be rebuilt from scratch at every layer. It also helps gradients flow backward during training. Layer normalization solves a different problem. As vectors move through the network, their values can shift in scale. Layer normalization recenters and rescales each vector, keeping the computation stable from layer to layer. So residual connections help information flow. Layer normalization helps keep that information well-behaved. Together, they make it possible to stack many transformer blocks without the model becoming unstable. These details may sound small, but without them, modern large language models would be much harder to train. Residual connections keep information flowing. Layer normalization keeps the computation stable. And together, they allow transformers to do the thing that makes them powerful: stack many blocks, layer after layer. Once these blocks can be stacked reliably, depth becomes the real power of the transformer. Each layer takes the representation from the layer before it and refines it. At the bottom, the model starts with token vectors. As those vectors pass through more layers, they become richer and more contextual. Lower layers may capture simpler patterns, word shapes, basic syntax, and nearby relationships. Middle layers can start connecting larger structures: phrases, dependencies, roles, who did what, which object belongs to which action, and which pronoun refers to which noun. Higher layers may capture more abstract signals: topic, intent, style, and what kind of token should come next. This is not a strict rule for every model, but it is a useful way to think about depth. Each layer does not start from scratch. It builds on what the previous layer already discovered. After passing through many transformer layers, a token is no longer represented as an isolated piece of text. It is represented in context, a vector shaped by the tokens around it, the relationships between them, and everything the model has built across the previous layers. That final representation is what the model uses to predict the next token. At the top of the transformer, the model has one final vector for the current position. This vector contains everything the model has built from the context so far. Now it has one job: predict the next token. To do that, the vector is projected back into the vocabulary. If the model has tens of thousands of tokens in its vocabulary, it produces one score for each possible next token. Then softmax turns those scores into probabilities. For example, after the cat sat on the model might assign mat, 62% floor, 12% chair, 5% and tiny probabilities to thousands of other tokens. Now the model has to choose. Sometimes it picks the most likely token. Sometimes it samples from the probability distribution. That sampling is controlled by settings like temperature. A low temperature makes the output more focused and predictable. A higher temperature makes it more varied and creative. Once a token is selected, it is appended to the text. Then the updated text goes back into the model. The transformer runs again. A new next token prediction is made, another token is selected, and the loop repeats. One token at a time, the response is built. That is generation. So why did transformers change AI forever? 3 reasons: context, parallel training, and scale. First, self-attention lets tokens build context dynamically. Instead of processing a sentence as isolated pieces, the model can decide which tokens matter for each prediction. A pronoun can connect back to a noun. A verb can connect to its subject. A word can change meaning based on the words around it. That ability to build context is the first breakthrough. Second, transformers are efficient to train. Older sequence models process text step by step, one word after another. That made training harder to parallelize. Transformers changed that. During training, attention can process many tokens at the same time. That made it much easier to train on massive datasets. Third, transformers scale: more data, more compute, more layers, more parameters. The same basic architecture kept getting better as it got larger. That scalability is one of the biggest reasons transformers became the foundation of modern AI. And they did not stay limited to language. Transformer-style architectures now appear in vision models, speech systems, video generation, multimodal models, coding assistants, and AI agents. That is why the transformer is not just another neural network architecture. It became one of the core engines behind modern AI systems. But it's also important to understand what a transformer is not. A transformer is not a database. It does not look up facts like a search engine. By default, a language model generates based on patterns learned during training. That means it can be fluent without being up to date. It can sound confident without checking a source. And it may not know private documents, recent events, or external tools unless another system connects it to them. That is why systems like RAG, browsing, tools, and agents are built around language models. They give the model access to information or actions beyond its internal parameters. A transformer is also not conscious. It does not understand language the way humans do. It processes vectors. It computes attention. It transforms representations. And it predicts tokens. But when you scale that machinery across billions of parameters and massive datasets, surprisingly powerful behavior emerges. That is the strange beauty of modern AI. A simple objective. A scalable architecture. Massive data and compute. And from that, we get systems that can write, code, reason, summarize, translate, and interact with the world through tools, not magic. Engineered scale. So that is the transformer. Text becomes tokens. Tokens become vectors. Attention builds context. Layers refine that context, and the final representation predicts the next token. Then the loop repeats. One token at a time, the response is built. That is the core idea behind modern LLMs. Not magic, not a black box forever, a carefully engineered architecture built from vectors, attention, and prediction. This is how transformers actually work. That's it for today. Like and subscribe so you don't miss out on more AI deep dives. See you in the next one.